Okay, welcome to the lesson 9.4, 9.5, really part one lesson. This is really going to be, I would think, for most people, that are an introduction to trigonometry. So obviously, I think this is one that you probably might have to go back and watch a second time. I'll try to keep it real straightforward for today. Really, the homework will have two types of problems, and we'll look at a couple different examples that go right along with them. So just make sure you're following along. This would be the portion, though. The next part coming up here is where we would be kind of taking the notes. So it's probably not going to hurt to maybe transfer some of this to like a notebook. For sure, at least you got to watch the video, because this is, I would think, brand new for just about everybody. So let's do it. First thing, just before we even get into trigonometry, parts of a right triangle. We've done this before. We've labeled stuff. The first thing I actually new here that I'm going to put in here is what's called, it's what's called theta. You see it a lot in trigonometry. It's like a little circle with the line through it. It's a Greek letter. Usually in trigonometry, it stands for just an unknown angle, an unknown acute angle. So that's kind of all that is there. It's called theta. Unknown acute angle. So that's kind of the first thing. You'll see those a lot as we get into some of the examples, some of the notes. So theta, just an unknown acute angle. Second thing, we've talked, I know everybody knows this is still called, we're not changing this, this is still called the hypotenuse. We'll abbreviate it in different spots, in HYP, or sometimes just even H. Okay? I know everybody knows it's the side that's opposite of the right angle. These two we've called legs, right? The two, what would have to be the shorter sides. Okay? We call the legs. We're going to be a little bit more specific. Instead of just calling them both a generic legs, we're going to call the side that's, I think let's start with the opposite side. If this is my angle, so it's all perspective here. If my theta, if my unknown angle is right here, if this is where I'm putting my theta and I want to talk in terms of theta, this down here we would be calling our opposite side, which we'll abbreviate, again, either OPP or sometimes just O. The side that's right next to me, so like this side right here, it's another leg, but instead of just calling it leg, we're going to call it the adjacent side, which we will abbreviate adjacent, or sometimes just really just a capital A. That's fine. So that's what we have to converse in: hypotenuse, opposite, and adjacent. The thing that sometimes people struggle with is right here. What happens if, let's move this out of the way so I can get some of these other things here. What happens if all of a sudden our theta is right here? Well, things change. Okay, hypotenuse will never change. That's always going to be opposite of the right angle. But right now, I've got these mislabeled, right? The side that's, if I were to walk out from my angle, this is actually now called the opposite side. And this one right next to me would be my adjacent. Okay, so it's all like kind of perspective depending on the angle that you're talking about. Okay, hypotenuse never changes, but opposite and adjacent will, depending on where your theta is. Okay, so that's a little bit of the vocab that goes along. They're not super tough words. Theta's new, but opposite would be like walking out from the acute angle. What side are you going to run into? Adjacent would be the side that's right next to you. Okay, opposite, adjacent, hypotenuse. All right, so let's get into some actual trigonometry. Trigonometry. trigonometric ratio is basically just taking one side length in a right triangle. This is all right triangle trigonometry, and putting it over, like in a fraction, another side. So taking however long the opposite side is, here's my theta, labeled just like what we talked about, adjacent, opposite, hypotenuse. If I take the opposite side and put it over the hypotenuse length, you know, maybe these are numbers, I'm going to get a trigonometric ratio. It's taking one side length and putting it over another side length. Take this side here and put it over this side in a fraction, you know, maybe a decimal number. That's a trig ratio. The thing that makes trigonometry so useful is that every acute angle in a right triangle has its own set of unique side length ratios. So kind of like we did with the 30, 60, 90 and the 45, 45, 90, how we put those side lengths, the 1, 2, and the square root of 3. So like if we were to just going back, refreshing, the 30, 60, 90 is not going to hurt us. In our 30, 60, 90, we saw that every 30, 60, 90 triangle has these different ratios of side lengths. So a 30 degree angle, we'll get into this in a little bit later. If I were to take the opposite length and put it over the hypotenuse length, it's always going to be 1/2 for every 30 degree angle. So we know some of these ratios already. Well, what happens when this is 31 or 32 or 33? Well, I'm not asking you to know all those. These ones we do have to know. 1, 2, and the square root of 3. And then for our 45, 45, 90, same thing. So again, for every 45, I take the opposite length and put it over the hypotenuse length. I know what that ratio is going to be. Every 45 has that ratio if you do that. So where trigonometry is kind of useful is that it's unique. This angle, whatever it is, if I take the opposite length and hypotenuse length, there's only one angle in the world that's going to have some of those numbers. We can figure out what this angle measure is. Okay, so that's kind of the basis of like a trig ratio, what it is. How are we going to use them? What do we need to know about them? Here's the deal. There's 3 that we have to know. Okay, and I'll show you easy ways to remember them. The first one, it's called sine, S-I-N-E, abbreviated sin. I'm sure have seen these buttons on your calculators before. The sine of an angle, of an acute angle, is all it is taking the opposite length, whatever it is, and putting it over the hypotenuse length. Okay, so that's one that we'll have to know, the opposite length over hypotenuse length. That's just the name for that orientation, taking the opposite length and putting it over the hypotenuse length. Okay, the other two, it's just a different orientation now. Okay, we're still talking about like an unknown angle here. If I were to take the adjacent length, some number, and put it over the hypotenuse length, then we would be talking about the cosine of an angle, which is just abbreviated COS. Again, we've seen these buttons on our calculators, hopefully. We'll get to using them here shortly. And then the third one, okay, is called the tangent ratio. What haven't we done yet? We did opposite over hypotenuse. We did adjacent over hypotenuse. We haven't put these two together yet. Okay, so which does it go? Adjacent over opposite or opposite over adjacent. Tangent is the opposite length over the adjacent length. Okay, so it's just 3 different ways of kind of organizing to the numbers. Okay, you may have heard this before too in other settings. I don't know. We do it in maybe even in algebra class. SOHCAHTOA. It's a nonsense phrase, but that's kind of like your go-to as far as how are you going to remember all 3 of these? Because it's a lot to remember. So how this works is basically S stands for what? Sine. The sine of an angle, of an acute angle, is equal to the O. Here's those big words then. Those same words that we talked about on the first slide. Is equal to, so the sine of an unknown acute angle is equal to the opposite length over the hypotenuse length. Okay, so this little phrase here is, if we can remember, it's SOHCAHTOA. Just say it a few times. Usually on the homework today, you probably write that on every single page, or at least it's just a single worksheet. But on any trig problem, you're going to want to see this. Cosine, the cosine of an angle, C stands for cosine, so we got to learn a little bit of this new vocab. Cosine of an angle is equal to the adjacent length over the hypotenuse length, and then the tangent of an angle is equal to the opposite length over the adjacent length. So there's the interpretation of this, what that means. Once you kind of get good at it, I would think you're probably not going to have to write all these out like this, but that's how we would use it. Okay. All right, a couple examples here. First one is just getting familiar with using, or just getting familiar with those three relationships. You can see, here's the question. Find the sine, cosine, and tangent of angle U. Okay, so we've got a couple acute angles here. I've got an acute angle U, an acute angle W. It's asking about U. Write each answer as a fraction and as a decimal rounded to 4 decimal places. Okay. So let's do this. Let's, like we've seen on the other pictures, let's put a little theta right here just to remind us, hey, that's what we're talking about. I think maybe even before I do that, it's a trig problem, sine, cosine, tangent. Those are kind of like trigger words there for us. We need to see this phrase that we just got done talking about, SOHCAHTOA. Okay. Because I think if I have that, I know all my relationships. It's just, you can see in the triangle, I know 34, 30, 16. I've got all these different numbers, and it's just situating them, this over this, or this over this, which, what's the order? How do they go? So we put a little theta at the angle that we're talking about, U. I think now the next thing I would want to do is label. Okay, so the side that's opposite of where we're standing, I'm going to call O. This side, freebie always, going to be your hypotenuse, and this side right here that's next to us is going to be our adjacent. So H, O, and A, just to kind of save some writing. I think that's an easy way to do it. So I think we have everything we need now in front of us. It's just a matter of kind of laying it out. Let's start with sine. So the sine, and let's call it angle U, because we're actually talking about a name of an angle. Sine of angle U is equal to, what's my relationship? The opposite length, which we've labeled opposite down here as 16, over, what's my sheet here? Hypotenuse length. Oh, I can see it right there. Hypotenuse is 34. Okay. Well, let's reduce it. Always reduce your fractions. So I've got a calculator here next to me. You should have one next to you. 16 over 34 reduces to 8/17. So we're talking 8/17. And then as a decimal to 4 places here, 8 divided by 17. I'm getting 0.47058, which will round up to 0.4706. Okay. You'll see in kind of future lessons why it's important to go a little bit further out, a few more decimal places than just to like 0.5 right now. Basically, what we said earlier, that whatever this angle is right here, there's only one angle in the world that has this number for its sine. And our calculator has it all stored inside of it. We'll figure out how to kind of coax it out of it. But there's a big difference between 0.4706 versus 0.5. So that's why I'm asking go out a few more places. Okay. All right. I mean, really all we have left to do is that same kind of pattern here for cosine and tangent. Okay. So let's do cosine. Let's set up the cosine. It's just asking, what is the cosine of angle U? Okay. The cosine of angle U has to be equal to, let's see, my adjacent length, which we're saying is 30, over, let's see, here's my sheet, over the hypotenuse length, which we have set from the previous one. You can see on here is 34. So we'll do the same thing. Let's reduce it. 30 over 34 reduces to 15/17, which if I divide it, I get 0.8824 if I round accurately. Okay, so I've got my sine taken care of, my cosine taken care of. One more to look at. It's just the third one. What's the tangent? So the tangent of angle U is equal to the opposite length over the adjacent length. Awesome. Let's reduce it. 8/15, which if I divide it out, 0.5 with the repeating 3 here, so we'll go out to our 4 decimal places. So that's the kind of the first part, is just getting familiar with SOHCAHTOA. How do I situate? How do I arrange stuff? Labeling your opposite, your adjacent, your hypotenuse, reducing fractions, rounding. Okay, I think very doable. So follow this example. It'll be like the first 1 or 2 questions on the homework. Next type of problem would be, okay, let's use these ratios to find an unknown. Okay, so now I'm looking at, it's a triangle, so some differences in setup here is, now I actually know the acute angle. I'm not going to use a theta because theta stands for unknown. Well, we know this is 31, so I don't need a theta. Before we do anything, we said, I'm not going to go back. This is our automatic, gotta see, want to have in front of me for any one of these. Okay, so SOHCAHTOA. All right, find the value of x, round or answer to the nearest tenth. All right, let's run through our progression. Okay, just so we can kind of see, how do we find side lengths in right triangles? Pythagorean theorem, not going to help me here, right? Just because I don't have enough side lengths to use Pythagorean theorem. It's not a 30, 60, 90, it's close. It's not a 45, 45, 90, so I can't use the models. And then it doesn't have the altitude like we saw in the last lesson, 9.3. So I can't split this up into 3 triangles and do stuff like that. So the only option I have here is going to be trigonometry. Okay, so here's kind of the process for that. All right, let's use some trig. I'm still going to want to identify the angle we're working with. So I'm going to put a little just stick figure here and say, okay, I'm standing at a known angle. Could I figure out what this angle is up here and stand there? Sure, right? 180 minus 90 minus 31 tells me this angle measure here. We could stand there, but we want to stand at a known acute angle, because it goes back to, okay, a 31-degree angle has only a certain relationship of side lengths that we can situate. Okay, so we got to stand at one that we know. So we're going to stand at the 31. Just like the last one now, because we're choosing to stand here, that makes this side over here my opposite. Use parentheses, I guess. My opposite, which kind of looks like a 0. My adjacent, and this side up here is always our hypotenuse. Okay? So there's some similarities as far as setups, right? We did this before. We used a theta. We labeled everything: opposite, adjacent, hypotenuse. Now we got to figure out which of these trig functions we want to work with. I don't have to use all 3. Really, there's only one that I'm going to want to use. Okay? So here's kind of the question you ask yourself. What do I want to know? Here we go. I want to know x, which we've called our adjacent. What do I know? I know my opposite. Okay? So there's only one pair up here, one of these 3 that have both O and A in it. It takes hypotenuse off the table because we don't know the hypotenuse. It doesn't help us. So that's kind of how we narrowed it down to, I want to be working with just tangent. That's the only one I need. Okay. So now I go to my setup of, all right, we decided on tangent. The tangent, not of theta anymore, of an unknown, actually of a known angle of 31, is equal to, what's the relationship? It's the tangent of a 31-degree angle always has to have the opposite length, which is in our case 17, over the adjacent length, which, how long is the adjacent length? I don't know. That's what we're trying to figure out. So there's my setup. The tangent of 31 has to equal 17 over x. It just has to. Whatever, my calculator has this stored in it. We got to figure out how to use it now. So stay away from the calculator for right now. All right, to solve this, we've been doing so much with proportions. I'm going to say, let's stay with it. This is just a number, some decimal number, but it's just a number in the end. How can I turn this into a fraction? Let's put it over 1. Okay, so now I'm solving for x right now. The trig part is the setup. Okay, how did I get tan 31 equals 17 over x? Go back and rewatch it. We talked through it. Now let's solve for x. So let's stick with cross multiplying. We've been doing a ton of that lately. Let's stay with it. When I cross multiply, obviously 1 times 17, that's kind of the easy one, the nice one. We'll take that. This is just x times tangent of 31. X times some number, tangent of 31. So keep them separate. This is no different. I'm going to do just kind of a little mini side problem over here. But if this was 10 equals 17 over x, how would you solve for x? Well, there's different things you could do, but maybe set this up as a fraction, cross multiply. 17 equals 10x, and then what would we do? We would divide by 10 to get x equals 1.7. Okay, same thing. This is still just a number. Okay, so how are we going to get rid of this number that's being multiplied by x? Well, we got to divide it. Okay, so let's divide both sides by the tangent of 31. Okay, don't touch the calculator. That's how we're going to get this to cancel over here. X is by itself. That was our goal. We were solving for x. So now x equals 17 divided by the tangent of 31. Now here's where the first time I'm going to touch my calculator. Our calculator does have all these ratios stored in them. It knows them. It knows what the ratio for 31-degree angles tangent always is. We just kind of had to get to a spot where we were able to use it to help us find a side lane. So I need to, first time touching my calculator right now, I'm going to go 17 divided by, and now I get to use that little tan button, the tangent of 31. My calculator says 28.29, so if we're rounding the nearest tenth, we're going to say 28.3 units. Okay, which I think is reasonable, right? This is 17, this just looks larger, so it should be longer. Sure, 28.3, I can buy that. Could we find hypotenuse now? Sure, I could use opposite over hypotenuse if I want to use sine. I could use Pythagorean theorem with this right now if I wanted to. But there we go, there's our first trig example of finding an unknown side length using, in this case, that's the way it worked out. We used tangent. Okay, let's look at one more, kind of for the day, for the lesson, and then we'll break and I'll have you try some. All right, find the value of x and y. So very similar looking figures, the last one, right? We got an unknown. It's cute. It's actually pretty close to the 31. First thing I'm going to want to look at is being able to see my SOHCAHTOA again, just so I can see it, right? Let's do the same thing as the last one. Let's kind of stand. Let's put a little stick person here at our acute angle. Label my opposite, right? This has to be opposite. This has to be adjacent. If we were standing here, these would be flip-flop, and this is always H. Okay? So far, so good. We actually have choice right now. Do we want to find X? Do we want to find Y? We could really find either one. I'm going to use trig to find both. Just it's going to stay a little bit more accurate. Let's just start with X because it's alphabetical. It's the first one up. So I want to find X. So I'm looking for my opposite. What do I know? I know my hypotenuse. There's only one combination up here that has an O and an H in it, right there. So now I've got to use a different one. I can't use tangent. It's not going to help me. I need to use the sine. So here we go. Similar setup as the last one, except we're using the sine of not theta, but of 26. That's why we chose to stand there, because we knew the angle has to be equal to the opposite length over the hypotenuse length. Okay. So there's a lot going into that, as far as labeling your sides, knowing what's what, opposite, deciding on sine, getting it set up right, opposite over hypotenuse. So that's the setup part of it, is getting it here. Sine of 26 is equal to opposite over hypotenuse. The solve portion. This one's actually a little bit nicer solved than the last one. Why? Well, I'm still going to do the same thing, but you can kind of see what's going to happen here. When I go to cross multiply, this one's going to work out a lot nicer. 1 times x is x. Sweet, the x is already by itself. Going the other way, just be careful how you type this. I would keep it kind of like we did in the last one, 14 times the sine of 26. You don't want to type it in as sine of 26 times 14, because a lot of calculators might actually do this first, and then what's 26 times 14? You're actually using the sine of 364. That's what 26 times 14 is, and we don't want to. We want the sine of 26. So just be careful on how you set that up there. I would probably write it like that just to avoid that. But we're ready to roll. Now I am going to my calculator a little bit earlier than we did in the last one, because the x was already kind of just set up by itself. It's basically going to be, when that's in the numerator, it's going to be kind of the one-step nice 1 times x. So let's finish it. 14 times the sine of 26 on the calculator. I'm getting about, let's see, we're going 10th again. Yep, 6.137. So I'll just round it to 6.1. And there's our x. Again, I think it's reasonable. It's not like 0.000, some weird number. And it's not bigger than this. So, I mean, I think it's reasonable if you're just kind of taking a step back and looking at your answer. Now, again, you could use this in a Pythagorean theorem, 6.1 squared plus y squared equals 14 squared. The problem with that is, and where I'd say I'd caution against that, is you're using a rounded answer. This wasn't exactly 6.1, right? It was 6.137. It's a little bit bigger than 6.1. So now I'm using a rounded answer to find another answer. I'm potentially going to have rounding issues depending on how much we rounded from here to here. So I'm going to show, plus we're in a trig lesson, so I'm just going to show, let's find y using, that wasn't that much work. It may actually be less work than a Pythagorean theorem. So just kind of starting from the beginning. We don't have to relabel. We can still stay here. This is still adjacent, still opposite, still hypotenuse, except now we are looking for adjacent. Okay, well, that's what we're looking for. And I want to still use this 14 because it's exact. It's clean. It's a whole number. So now I'm looking for the function that has a and h in it. Okay. Well, that's cosine. So similar setup. The cosine of where we're standing, 26, is equal to the adjacent length, I don't know it, over the hypotenuse length. And again, I would definitely argue that this is going to be less work than a Pythagorean theorem. It's going to be cleaner. It's going to be better numbers. They're all 26, 14. We're not using this rounded 6.1 because the cross multiply, you can see 1 times y, just like the last one, the y is in the numerator. Y is equal to 14 times the cosine of 26. So other than me now at this point kind of grabbing my calculator and saying, okay, 14 times the cosine of 26 equals, calculator says 12.58311, so we'll go 12.6 on the round here to the nearest tenth. And again, it's reasonable. It's bigger than this side. It's less than the hypotenuse, so I think my answer's within the realm of possibility here. And there we go. I'm sure if you did Pythagorean theorem, it would be really close. You'd run into the issue of maybe having like a 12.5, but my answer key is going to say 12.6 because that's what it is. All right, so we're going to break here. We're going to call that 9.45 part 1. I'll get you an assignment that kind of goes with those same 2 types of problems there, where you're going to practice basically kind of just laying this out, a triangle. Here's the difference where you knew all 3 sides and just kind of getting stuff situated the way they went, side lengths over side lengths. And then the only other problems on there are, I'm going to give you a right triangle with either 1 or 2 unknown side lengths and say, hey, find the other one. So your work should be like this. Remember, there's 2 solves. These we saw in that third example. These were the kind of the 1-step solve, cross multiply, variable is in the numerator. Versus if that variable on the previous example 2, was in the denominator, that's kind of a 2-step one there. So go through and show that 1 times 17, x times tangent of 31. We weren't done yet. We had a second step. Get that x by itself, divide everything in this case by the tangent of 31. So there's 2 really kind of different solves you're going to see. So go back and rewatch if you need to, and look for a part 2 lesson coming in the next couple days. All right.